Okay, welcome to the 10th lecture of EP1027, Maxwell's Equations, Electromagnetic Waves. This lecture was scheduled actually yesterday, April 28th, but my voice wasn't so well yesterday, so that's why I'm recording it today. Today's lecture will be released sometime tomorrow. So the agenda for today's for the lecture is the following. I'll first review what we covered at the end part of the second half of last lecture, which is I'll remind you the basics of the wave equation in one dimensions. And there are a couple of solutions, special form of solutions, which are important for this course. One is D'Alembert solution, which I will remind you, and Bernoulli solution, which is of sinusoidal waves. And then we will use the superposition principle to write down the general solution. I'll also review electromagnetic waves in vacuum and matter. This is basically what I'll show, that the Maxwell equation reduced to three-dimensional wave equation in the absence of charges. So electromagnetic waves will just be oscillating electric and magnetic fields. And then I'll talk about the new topic which I will begin today is what happens when EM waves are incident on an interface or boundary of two media. What are the laws of reflection and refraction for the EM waves, and that will turn out to be coincident with the laws of reflection and refraction which you'll learn about in optics, light ray laws of light reflection and refraction of light rays, which you learn in optics in high school. So we will see a nice derivation of that in terms of Maxwell theory. And then I'll talk about Fresnel equations, which are the equations which govern what fraction of the wave is transmitted and what fraction of the wave is reflected at the boundary. And then I'll move on to talk about electric field in conductors, in which EM waves will be passing through. And as it turn out, EM waves which are oscillating electric and magnetic fields, they will not be able to make much progress inside conductors, and they will only be confined to a very thin skin around the surface of the conductor, an effect which is known as skin effect. And this is an important effect. So unlike in steady currents, when conductor can carry, current can move, electric field can move through the bulk of the conductor, we will not be able to see that. And then we will see the similar thing which we did for EM waves when it was incident on a boundary of two dielectric. In this case, we will study a reflection from a surface of a conductor. That is, we will study the EM waves incident on the surface of a conductor from a dielectric. So one side is dielectric, the other side is conductor, and we'll see what happens. Most of you know the answer. Most of the EM wave will get reflected straight back, and that is the special thing about conductor, but we will see how that actually happens. So the references of reading for this chapter, for this lecture, is Griffith's chapter 9. This contains most of the wave phenomena. So this is a review of wave motion. As I introduced in the last class, the wave equation looks something like this in one dimension. So there's a spatial derivative, second order, and there's a time derivative, second order. And this the wave variable is called the wave field parameter, something which is oscillating or not oscillating, which is varying with space and time. Oscillating are a special case, we will see that. But in general, it's a function of space and time which obeys this equation. So this number v, which appears with dimensions of velocity, is actually the phase of the wave, velocity of the phase. So that's why it's called the phase velocity, or some people just call it the wave velocity. The solution of this equation is remarkably simple. It's a second order hyperbolic PDE, but the solution can be easily obtained by taking a clever change of variables from x and t to x plus t and x minus t, and x plus vt and x minus vt, as you can see here. If you write in those equations, this equation becomes very simple to solve. And the solution was obtained by D'Alembert a while ago, maybe 2 or 3 centuries back. So he showed that the wave field parameter can be written as the sum of two arbitrary functions of the variable x minus vt and x plus vtg, and h are arbitrary functions. It can be completely arbitrary. They're only fixed by boundary conditions. They're not really determined by anything else. So x minus vt, you can think of it, it's if you compute the velocity of this object, dx dt is equal to v, and x plus vt, you can compute the velocity of this thing, dx dt will be minus v. So this is the left moving wave and this is the right moving wave, because this is positive velocity and this is negative component along the x-axis, negative velocity along the x-axis. Okay, so this is the most general form of the one-dimensional wave equation. We also noticed that the wave equation is a linear equation. That is, f appears in only linear power, and there is no f squared or f cube appearing here. There are no product terms. So as a result, most of you know what happens if you have a linear differential equation. If you find there should be fi here. So fi's are different solutions. If you have a lot of different solutions, you can superpose with arbitrary coefficients ci, arbitrary constant coefficient ci, and that will be a generic solution of the wave equation. So using this phenomena, we can construct more general waveforms. Another solution which is very widely used is something which is known as Bernoulli Solution, in which the waves f and g, these are taken to waveforms are taken to be sinusoidal. So Bernoulli Solution looks something like that. So fxt, the left moving component is to be taken in this way, and the right moving is this. G is taken to be a cosine function, and h is taken to be another cosine function. However, we will, in all generality, we will keep this constant delta 1 and delta 2, which are the phases. Omega here, so x minus vt we have replaced by kx minus omega t. So it is clear from this that omega must be equal to k times v. So omega sometimes is known as the angular frequency. Most of you know k is known as the wave number, which is twice pi over the wavelength, and v the phase velocity. So this equation is also written in sometimes which you learn in high schools. The wave speed equals to frequency times the wavelength. So better than writing it in sinusoidal waves, we will write these things in a complex notation. The Bernoulli solution can be written in a complex form, which is much more advantageous, because as you know, most of you know, if you take derivative and integrals of the exponential, which remains the same, it's very easy to work with exponential functions. So we will take f to be the real part of f tilde. Anything which is tilde will mean a complex quantity. In this lecture especially, if you see a tilde over anything, that means it's a complex quantity. So if we do that, for example, let's look at the first. Let's look at this part. So this is the real component of this quantity, but delta 1 has been absorbed in a. Okay, so a times e to the delta, which was appearing here, exponential of I delta, that has been absorbed in the amplitude. So the amplitude will know about the phase information. Anything which doesn't depend on space and time, that phase we will absorb in the amplitude. So this is another great thing about the complex notation, is that the amplitude can become complex and it remembers the phase. The phase information can be tracked by looking at the amplitude. As I said, that any arbitrary wave solution can be written as a superposition of many different wave solutions. What I wanted to say is the converse, actually. If you have a bunch of solutions to the wave equation, you can take an arbitrary linear combination and they will also satisfy the wave equation. This leads to the reverse scenario, in which any arbitrary solution can be expanded in a basis of preferred functions, and those functions we can take to be sinusoidal functions. Okay, so we will take sinusoidal. In fact, we will take them to be exponential. So any arbitrary wave solution, not necessarily the Bernoulli solution, but the most general solution, D'Alembert solution. D'Alembert solution can be written as a generic superposition of sinusoidal waves, something like that. Okay, so I've summed over all possible k's and omega, but omega is equal to k times v, and v is constant. So sum over k automatically means sum over omega. So in this basis, in this exponential basis, we're expanding a generic wave. Also, in order to fully solve this, we will need boundary conditions. Most of you know from high school that when you have a wave, one-dimensional wave, for example, a kink which is moving down a string, and if we have two strings which are joined at a particular their ends, then we have a boundary between two media. And whenever the wave is transmitted through, you will remember from high school that the frequency of the incident, reflected and transmitted wave at some boundary is the same. Most of you know the reason why this should happen, but let me just repeat it. The reason is that most of the sinusoidal waves are actually happening because the constituents of the medium are undergoing some kind of forced oscillations or oscillations. And whenever you have forced oscillation, usually the oscillation frequency corresponds to the one with which the forcing function, the external force which is causing it to oscillate. So the whole system sort of oscillates in the same frequency as the external influence. So in this case, that's why the frequency of the wave which is transmitted or reflected will be the same as the incident. The incident one is the one which is the cause, and these two are produced as a result. This will have the same frequency as that of the cause. Of course, that means if this formula is to be trusted, if I keep if I keep omega to be the same, and if we have different k, then so the only way you can have this is, well, k and v can change. You might ask, well, what about the situation when k and v do not change? And then we're talking about the same medium. But if you go to a different media or a different string, usually the wave velocity is determined by the elastic constants that will change. As a result, the wavelength will also change. So this is what I wanted to say. And then after this very short summary of wave equation basics, I move on to electromagnetic waves in vacuum. So in vacuum, when you have no charges, Maxwell's equation turn homogeneous. So there are no sources anywhere, so divergence of E equals divergence of B equals 0. And these two are the Faraday Law and the Ampere Maxwell Law. From these, if you take curl of the last two equations, you end up with the E and B fields obeying some kind of a wave equation, three-dimensional wave equation. Instead of del del x square, ddx square, you have the Laplace operator. So this is a 3D equation. So it just tells you that EM waves, which are actually will turn out to be oscillating electric and B fields, as we shall see in a moment. So these obey some kind of wave equation. In particular, the wave speed or the phase velocity of this EM wave is the speed of light in vacuum. See, if you remember how the speed of light came about, it came about when we were talking about point charges moving and producing magnetic fields. And the equation for the magnetic field produced by a moving point charge had factors of the speed of light coming due to transformation of frames from the rest frame to the moving frame. That is why we had Maxwell's equation had the c square everywhere. There was no apparent connection to light. It came through special relativity when we go from one frame to the another inertial frame, moving frame to rest frame. So it turns out that EM waves move with the speed of light, and from this Maxwell concluded that light must be EM wave. Light must be an EM wave. Okay, so now let's look at some solutions. Now the solutions we will be interested in are plane waves, in which the wavefront is planar. So the wavefront is the surface of constant phase in any wave, and we are looking at plane waves, in which case the wave surface, constant phase surface, is a plane, and a plane has a normal direction, as you know. So this normal is the direction of propagation of the wave. So this is the generic way of writing the solution. So these are not just plane waves, these are also monochromatic waves. That is, k is a single number, there is no superposition over all k. Okay? K is the wave vector, this is normal to the wave fronts. So you can show that the solution of planar wave equation, I'm not going to solve wave equation to you, I'm just going to show flash the solution. And this is the solution. Whenever, as I said, that whenever I write a tilde over something, usually that quantity is complex. In the special case, it can be real also. But generically, whenever I have a tilde over anything, I usually mean it has a complex phase or a complex component. It has an imaginary component as well. And this part is the phase part of the wave, which is the space-time dependent. So I've taken this to be a right-moving wave. You can say the velocity will be plus. Actually, in 3 dimensions, there is no outgoing. There is no right-moving. However, you can see that x is increasing with time, so that you can think of this as a spherically outgoing wave. And then if I had a plus 1, it would have been a spherically incoming wave. Okay. Now this kind of a wave ansatz or wave solution we will plug in this equation. So these were the solutions obtained from looking at these, and now we're going to plug it in these individual equations to gain some more information. So Gauss law and no sources of Sinks law, this equal to 0. Both of them give you, whenever you take derivative with respect to space, because of this exponential function, this k will come down, k vector will come here. So that will give you k dot e, and this derivative will give you k dot b equals 0. You might ask at this point, you might be a bit more careful and ask, well, why am I supposed to take E and B to be the same frequency and oscillation? E and B obey seems like two separate equations. This form is the same, but can I not take in general K and K here and K here to be different? The answer is yes, you can take that, and in fact you should probably, K1 and omega 1 and K2 and omega 2. But then the equations, the Maxwell equation will relate E and B, and then you'll be inevitably led to the conclusion that they have to be the same. So yeah, in general they can be different, but this Maxwell equation relates them to be the same. In particular, you can show that the wave vector is orthogonal to both E and B. So EM wave is a transverse wave. And then we can apply the Faraday Law, which will tell you that B equals wave vector unit vector along the direction of propagation times E over C. So this tells you that E, K, E, and B, these form, or E, B, and K, they form an orthogonal triad. Maybe I should have had a picture here, but we will see in one of those slides. What happens is, let me just, yeah. So if this is the direction of propagation, E and B are orthogonal to K, and you can think of this as this constant phase surface on which E and B have the same phase. Okay. So this is very important, because if I take magnitude of both sides, this tells me B is E magnitude of E over C. So B is much weaker than C because C is a large number. However, we can show that the energy contained in E and B fields are the same. So because you have this relation, you can find out what the energy stored in magnetic field per unit volume is. And if you plug in this number, you can easily show that this is equal to the same as in the electric field, energy contained per unit volume in the electric field. So this is what I've written here. Little u is the energy density, and the subscript E means the energy density contained in electric fields, and then the corresponding u subscript B means the energy density contained in magnetic fields. So these two are the same, and you can have total energy, which would be the sum of these two. The factor of half will go away. So the total energy contained in E and B fields is something like that. So you can compute the Poynting vector. Most of you know what that is by now. Poynting vector gives you the energy flux density, right? Energy flowing per unit area per unit time. And this is the energy, because it's energy current actually per unit area per unit time, per unit area orthogonal to the current. So the energy is flowing in this direction, E cross, most of you know the expression for S, which is E cross B over mu naught, but E cross B is same as the wave vector K. So not only is the phase transported along K, but the energy of the wave is also being transported along K. This doesn't always happen. We will see in some other media where wave energy is not transported necessarily along the phase. And this is a bit of a special case. So here what we see happily, phase and energy being transported in the same direction by K hat, and this is the amount of energy which is being flowing per unit area per unit time. Okay. Similarly, you can compute as you have computed the energy contained per unit volume, you can contain the momentum contained per unit volume. Momentum has component, so it will be a vector. So most of you know from last few lectures that is also given by the Poynting vector divided by c square. So this is the energy contained, momentum, linear momentum contained, and we can see the linear momentum is entirely directed along the wave vector. So orthogonal to this, there is no linear momentum density. The entire linear momentum per unit volume is directed along the wave vector K. So not only the energy, but the linear momentum is also of the wave is also along the wave vector. In particular, what I've written here is that basically the fact that Yeah, from this expression you can see when we divide by c square, what you get is that momentum density is energy density divided by c. Some of you who have taken special relativity will remember that this also happens for a particle where P is E over C. Okay, so next thing is the pressure exerted by EM waves. So when EM wave is incident on a surface, let's say an absorbing surface in particular, then the surface absorbs the EM waves. In particular, it also gets the momentum which is contained in the EM waves. It is being absorbed. As a result, momentum is transferred to the absorber. And whenever you have momentum being transmitted, it exerts a force. In this case, we can compute the pressure, which is the normal force exerted on the absorber per unit area of the absorber. Now, normal force will be equal to the force of the momentum transferred per unit time by Newton's second law. And then momentum transferred per unit time, we can compute this by imagining a process. Let me just draw it. Let's say this is the absorber and this is the EM wave. Now in unit time, what amount of the volume of the wave is incident per unit area? You can imagine a cuboid with cross-sectional area being equal to unity and length c, because that is in unit time. C is the length of the rectangle which will crush into this absorber, which will be absorbed into this absorber. So C times unit area is the volume in which the momentum of which is entirely absorbed by the wall. So C, that's why I have to multiply by the volume and the momentum density. So this is the momentum density times volume will give you the total amount of momentum which is absorbed per unit area per unit time. And from the previous expressions, previous page expression, we know what this quantity is. So this is equal to C epsilon naught E square, but look, there's an extra factor of half. This extra factor of half comes because I'm doing an average over time. And remember, this is the oscillating quantity. This is the oscillating quantity. So this is an oscillating quantity. So E square will be this square times square of this guy. So it's better off we take an average over one period or one cycle of the EM wave. And if you do that, most of you know that the expectation value of E square, where E is sinusoidal, sine square, the average over one cycle is half. So that's why this explains the factor of half here. Okay. If you have a perfect reflector instead of an absorber, unlike for example a conducting surface, which we will learn later, then the change in momentum is twice, because not only the incident wave transfers its momentum to the surface, it gains equal and opposite momentum from the surface. So the net momentum transfer to the surface is actually twice of this. So then this half goes away. Okay. So and there is a microscopic picture to understand why this radiation incident on a surface leads to such kind of pressure. And that can be understood if you consider the fact that the surface is made up of constituent electrons and point charges inside. The idea is when an incident wave, EM wave, is incident on this, what happens is that the E and B field will drag the charges around. In particular, E will, for example, try to drag the charge around in this direction, in the top direction, and then the Lorentz force V, it will develop velocity in the vertical, and there will be a Lorentz force V cross B, which you can show V cross B. So V cross B is again in this direction. So the conductor will experience a force in the K direction. Okay, so it will experience a force in the K direction. So this is the origin of the radiation pressure when a wave is incident on a surface, absorbing or reflecting surface. Okay, so then one slide which I covered very quickly, but today I'll do it a bit more slowly, is the EM waves in matter. For that we need to start with equations, Maxwell equations in matter, which are these equations. Notice that all the right hand side is 0, so we have removed the sources in the absence of sources. In the absence of sources, we have 4 homogeneous equations. And then we pull the same trick, which is actually we will, before we do that, we will consider the case of linear homogeneous media. Okay, linear, not just linear homogeneous isotropic media. Okay, in such case we have the constitutive relations, that is D and H get related to B through these formulae, and if we plug in these, then we have an equation for just in terms of just E and B. Okay, so E and B, nothing else. And then again we can go through the same process as we did for EM waves in vacuum, that is, take curl of these two equations, and those will lead us to Maxwell equations. Those will lead us to the same wave equation as before. This kind of wave equation, the only difference will be the speed of light will not be there. Instead we will find, and we won't do this because of this quantity is there, you will not get the speed of light. Instead, you will get a quantity velocity which is proportional to 1 over square root of mu naught, mu times E, where mu is the permeability and epsilon is the permittivity of the medium. This quantity is because mu is permeability of vacuum, not permeability of the media, and epsilon. So this quantity is these two quantities are more than one. Mu is greater than mu naught and epsilon is greater than epsilon naught. So inverse of that will be greater than, this is greater than 1 over square root of mu naught C epsilon naught, which is the speed of light. So so the way we quantify this is we write V to be the ratio by which it is less than speed of light. So C divided by some number which is greater than 1. Okay. So this is a nicer way of writing the velocity instead of these epsilon and mu. So this quantity n, the fraction by the number of the times, I don't know how to best say this, but it's the ratio of the speed in the medium to the, ratio of the speed of light in vacuum to the speed of light in a different media, in a media, that is called the refractive index. Most of you are familiar with this quantity from middle school. I don't need to say much about this, but maybe in the topic of optics, but we will see this appears mostly in electromagnetic fields and matter in linear homogeneous isotropic media. Energy density is given by this general expression, and we can use the constitutive relations and reduce this to this form, which looks very close to the vacuum form, except instead of the vacuum permittivity we have the permittivity of the medium, and instead of vacuum permeability we have the permeability of that medium. Energy flux rate, which is the Poynting vector, that is given by this quantity S. It is actually given by E cross H, but we're using the constitutive relation B equals mu H. We can write it E equals B over 1 over mu. Now, again from the Maxwell equation, if we just had this for vacuum, for example, this Maxwell equation, the Faraday Law, you can show that this, most of you know, if you insert a plane wave, this curl operator will become the K operator, because the spatial derivative will bring down a power of K from the exponent of the phase, and the time derivative will give you an omega or something like that. So you'll arrive at this equation, B equals K hat, which is the wave propagation vector. Now I'm talking about a plane wave, times E, or cross E, vector product cross E, divided by the wave velocity V. Remember, this wave velocity now is different from speed. It's the speed of light. It's actually C divided by some refractive index. One last thing which we'll need before we move on to the stuff we wanted to discuss today, as well as the new thing, this is all a review, is the boundary condition at the interface of media. This will be important when we are considering EM waves incident from one media to when it's moving from one media and it is incident on the surface or the boundary of that media with some other media. So in that case we will need, in order to work out the equations which will give us information about the transmitted and reflected wave, we will need these boundary conditions. Most of you recognize what these are. As I said, this is in the absence of charges, so everything will become continuous. In particular, the normal derivative of D and normal derivative of B will be continuous. Also the tangential component or component of E and the tangential component of H, in which case this is B over mu, that will be continuous. So as I said, that the normal is one direction because the two-dimensional surface has a unique normal, but the tangent vector it's a two-dimensional surface, so it has two tangent vectors. That's why I've written in these equations, the parallel equations, in vector form. Okay, so this is the typical situation. As I said, I was interested in EM waves traveling in one media, and it becomes incident on the boundary with another media. So here we have that situation. We have z equal to 0. So the xy plane forming the boundary between two media with permittivity epsilon 1 and refractive index n1. And the second media has the other one with subscript 2. So this is a situation, a plane wave which is traveling in medium 1 is incident on this interface. So this is the incident wave. And then part of it is reflected and part of it is transmitted. Sorry. So this Ki, Kr, and Kt, this given by these blue arrows, give you the direction of give you the wave vector. Okay. And then the orthogonal to that we have the electric field components. They form out, EB and K form an orthogonal triad. So this particular diagram is not the most general diagram because it shows that the wave vectors are contained in one single plane, two-dimensional plane. So this will have to be derived. You cannot right now. I cannot justify this, but except that I cannot draw a full 3D diagram. That's why I had to draw it in this way. And also look that the E's are all in the same plane as the plane of the paper. So that is also not the most general case. E's could be orthogonal or could be at some oblique angle to the plane of the paper. That is entirely possible. However, I have only shown the in-plane polarization. So this component of E lies entirely on the plane of the paper, or plane of the screen. So this we will consider this case in the off-plane or orthogonal direction. I will give it as a homework for you guys to work out. So keep this picture in mind when I talk about the next few slides. In the next few slides. So here we have monochromatic waves incident on the interface from the left, which is this one. E and B are given by these formula. So E is so E0 is the complex amplitude, and I means incident. The subscript I here means big I means incident, and then the phase is Ki dot x minus omega t. Now omega, there is no subscript I because, as I said, when we have the phenomena of a wave approaching a boundary with another medium, all the transmitted, reflected, and incident waves, all three of them have the same frequency. That's why I didn't bother to put subscript here. So only the wavelength changes and the velocity changes. Okay. So this is the electric field, and then the magnetic field can be worked out by this equation, which basically follows from Faraday Law. The reflective wave, similarly, we can write down an expression for the reflected wave. So this is the reflected amplitude, this is the reflected phase. Again, frequency remains the same, but the wave number changes, and B is given by this formula. We can write down similar thing for the transmitted wave. Now, how do we relate these two? We relate these two through boundary conditions. But before that, I wanted to say that the frequency is same. But the frequency from the wave equation, it follows that frequency is K, magnitude of K times V. Let me just go back in some of the first slide where we had this equation. I think it was a while back. Yeah, so when we wrote down this form, sinusoidal form, we had K and omega. But here in 3 dimensions, you will have, instead of Kx, you will have K dot 3-dimensional position vector x, 3-dimensional K vector. In this case, this formula, which is sometimes known as the dispersion relation, this formula will change to omega equals magnitude of K times V. So magnitude of K times V. Okay. So if that is the case, what we can show is that the magnitude of the wave vectors of the incident and reflected will be the same, because for them the velocity is the same in that medium 1, while kt, the transmitted wave vector, The wave vector for the transmitted wave will be given by omega over v in the second medium, which is v2. And then in terms of the refractive index, we can write it in this way. Okay, it's n2 over n1 times ki magnitude. Okay, so we take the interface of the media to be the xy plane. This I already explained in the diagram. So the interface to be the z equal to 0 plane. So the z component goes away. This is the k dot x in the phase. So all of them have this k dot x kind of a term. So this k dot x will be 0. Sorry. K dot x to be 0. So then the only two terms which survive are kx, x component of k times x, and the y component of k times y. And this we can write in this form, which is k parallel dotted with x. Parallel component means which is parallel to the interface, and since the interface is the xy plane, k parallel is this kxx plus kyy. So subtracting the normal component. So generically, boundary conditions for Maxwell's equation that the interface, that is equal to 0, generically looks like this, right? So let me just go back. So you will have such kind of an equation. Now electric field in the first media would be the sum of the electric field due to the incident wave and the reflected wave, and here it will be the transmitted wave. So this is exactly what we have here, some incident plus some reflected. These coefficients contain the amplitude as well as the information about the permittivity and all that for all x, y, and t, right? So this should be true for all points on the interface. Now this x vector now is the parallel component. Remember, parallel to the interface, so only x and y. So this equation must be true for all x, y, and t, right? So since this is a complex equation, the phases on both sides must be equal. So if I take the amplitudes to be real, this just means that these part e to the minus I omega t, this part cancels. However, these terms won't cancel, and the only way this expression can be equal is that this component, this phase is equal to this phase is equal to this phase. Only then they cancel out. Only then this equation is consistent. Otherwise, it is not. You can have different phases for two quantum numbers. The different phases cannot be equal. So we have this happy situation in which for all x and y points, so all values of x and y, and z equal to 0, we must have this equation. Okay, k parallel dot x, k parallel dot r, k parallel r dot x, and k parallel component of the transmitted wave vector. These three should be the same. So in fact, that means for all x and y, if this is true for all x and y, you know, for vector analysis, if the dot product of two different vectors with the same third vector is true for all vectors x, then there is no other choice but these two vectors have to be the same. So that means the three k's, the parallel component of the wave vectors must be the same, incident, reflected, and transmitted. The parallel component must be the same. So this is sometimes known as the first law. This will lead to the first law of optics, or first law of reflection and refraction together, that all three wave vectors lie in a plane, right? So why is that? Let's remind you, the parallel components are all the same. So let's go back to the diagram. So the components of k which are parallel to the wave vector, parallel to the surface, which is the xy plane, they are identical, and then of course the normal lies in the z along the z-axis. So the sum of these two, the parallel component and the normal component, all lie in the same plane. Okay. Also, you can write this in terms of components, in terms of the parallel component. You can write in terms of the magnitude and the component of the vector along that. So it's very clear from the diagram that the normal component is proportional to cos theta. So then the parallel component will be proportional to the sine of each of these angles. So that's what we have. Sine theta gives you the parallel component. So these three should be the same. Now, from this equation, it follows the second law of reflection follows, and refraction as well. But let's look at the reflection. So then we consider just this first equation. Now Ki and Kr are the same, which we established some time back. Ki and Kr are the same because the frequencies don't change and the waves of speed in the same media remain the same. What we have, Ki is cancel out, and then the only solution is theta I should be equal to theta r. Thus the angle of reflection must be equal to the angle of incidence. Okay, and then for the third guy, when you have these two, then we have sine theta I. Theta r is same as theta I, so sine theta I over sine theta t equals kt divided by this magnitude of kr, which is same as ki. And this we saw nothing was this was equal to the, because the frequency remains the same, it will be v1 over v2, which is n2 over n1, right? The refractive indices of the two media. So this is sometimes known as Snell's law in optics, refraction. However, we see it's a straightforward result which follows from Maxwell's equation. There's nothing more complicated than that. In optics, you'd never really learn the derivations, but you just learn that all the experimental observations. But using Maxwell's equation, we can actually show that this is indeed the case. Okay, so now this is all fine. Just by looking at the phase, we can gather so much information. Now we haven't even yet fully looked at the boundary condition. All we looked at was the typical boundary condition and the phase information. But there is the amplitude information as well, right? The amplitude information will give us some knowledge about how much the wave is reflected and what fraction of it is sent back, or how much of it is transmitted and how much of it is reflected. So these are the equations. Now, because 3 is the z direction, normal component of d is continuous, normal component of b is continuous. Let's write down those equations. So the normal component of E can be written in this way, and the normal component of B, which is given by K cross E. So B, as we know, can be written in terms of E. Since we are considering the in-plane electric field to be on the plane of incidence, this is known as the plane of incidence. On the plane of incidence, the B should be orthogonal to. So because K, E, and B form an orthogonal triad, you can imagine B to be pointing out towards someone looking at the screen. So out of the screen towards the person looking at the screen, right? So this is the direction of B. So that is the direction of B. And one can compute the normal component of that. Let me just go back to the equations. So normal component of B is 0, right? Because B is orthogonal to the plane of the incident. So it is completely orthogonal to the plane of parallel to the interface. Yeah, B is pointing out from the plane of the paper, so it's parallel to the x and y direction, so it has no normal component. So the second Maxwell equation, second boundary condition, which is normal component of B is continuous, that will not really play any role because Z component is 0. So we have 3 equations basically, and these are the 3 equations. Now the first one, as I said, the normal component of D is D is continuous, which would mean epsilon times the normal components of E, which is given by this. You can work out from trigonometry what these are. And then the tangential component of E is also continuous, which is going to be cos theta. You can check these. This is the normal component and this is the tangential component. And the third equation is the x and y components of B or H as continuous. And using constitutive relation, you can write down as B over mu1. So you get this equation. Right? B will not feature because B we're writing in terms of K and E. So B itself doesn't feature at all. Except the third equation, second equation doesn't apply. For the other cases, we have these 3 equations. In these 3 equations, how many unknowns are there? Well, there are 3 unknowns because EOI, EOR, EOT is there. And then we have 3 equations. So this should be a solvable set of equations. So we can solve these in terms of some quantities, alpha and beta. So let's define for our convenience alpha to be this ratio of the cosine of transmitted angle to the cosine of the angle of incidence. This ratio we shall call alpha, and these two equations, I think these are the first two equations we can rewrite in terms of alpha and beta, or maybe it's the first and third equation. I don't exactly remember. Let me just think. Yeah, I think it is the second. These two equations I'm rewriting. So in these two equations you have cos theta, and the other equation you don't have any angle but just these ratio of velocities and permeability, right? So the third equation can be written in this way, the second equation can be written in this way, and then we can solve for the ratio, which is this. Okay, so this gives you the ratio of the reflected amplitude to the incident amplitude, and ratio of the transmitted amplitude to the ratio of the incident amplitude. So these are given by in terms of this coefficients alpha and beta. Now this is just for the in plane. So as a homework I would suggest you guys do the off plane component as well, in which let me just go back to the diagram. Yeah, in this diagram, instead of E, the B's will be on the plane and the E's will be orthogonal to the plane. Okay, so you should work out as an exercise whether a good way to understand that you follow all what I'm saying is by repeating the same exercise for the off plane components of E, polarization of E. So we have this equation, and then one interesting curious fact which I guess you've already learned in high school is that when you have alpha equals beta, the reflected wave goes to 0. The amplitude of the reflected wave is 0. That is, there is no reflected wave. Okay, the entire thing is transmitted when alpha is equal to beta. So that angle is sometimes known as Brewster's angle, that angle of incidence when alpha is equal to beta. So you equate these two. Remember, cos theta t is not an independent variable compared to theta I, because Snell's law already tells you what theta t should be when you have theta I. Snell's law already determines this. So when you equate these two, it will give you a special value of theta I. So that particular angle of incidence is known as the Brewster angle, which you have already learned in optics, I guess, in high school. But this is much more solid derivation in terms of EM theory. Now, physically, most of people know what this represents. Most of you have learned this in high school. Because light is a transverse wave, what happens at Brewster's angle is that this angle between the transmitted and the reflected component becomes 90 degrees. So this angle, which is complement, so this is theta r, theta t, and then the in-between angle becomes 90 degrees. As a result, the wave motion here, if some part of it is transmitted, but the transmitted component becomes parallel to the direction of the reflection. And since you cannot have a wave which has oscillation in this direction, which is the direction of propagation, you cannot have a wave there, because then it would become a longitudinal wave, whilst light is a transverse wave, right? So when the angle is such that the reflected and the transmitted makes a 90 degree, we will only have the transmitted wave, but not the reflected wave. Okay. Okay, so this is where we will stop talking about media, dielectric media. For example, one example would be glass or water. So all the relevant optical phenomena can be explained using these equations from electromagnetic theory when we're talking about materials such as glass or some kind of fluid or water through which light is traveling. However, as I said, there's another class of media which are equally interesting, which are conductors. So we will look at the situation when we have EM waves in conductors. So by definition, conductors have a lot of free charges, rho f. We can connect it to wire it up to a circuit, and that will introduce a lot of free charges in the conductor. And then we'll consider ohmic conductors, not perfect conductors, ohmic conductors, which are given by J free equals sigma E. If they were perfect conductors, the sigma will be infinite. But since we are considering real life conductors, sigma is a large number, but still it's a finite number. So ohmic conductors have this relation which is known as Ohm's law. Most of you are by now familiar with what Ohm's law is. So the free charge density is given by sigma times applied electric field, or not the applied electric field, the electric field which is present in the media. So Maxwell's equation for conductors. So the conductors will have some permeability. In addition, it will be given specified by a third number, which is the conductivity. Okay, so dielectric is specified by just two numbers, but the conductor is specified by all three numbers, epsilon, mu, as well as sigma. So the Gauss law looks something like this, and then this is Faraday's law. So no sources of Sinks law, and then this is Ampere Maxwell law. Now, Ampere Maxwell law, instead of mu times J, I have put this because J is equal to sigma times E, right? So this was curl of H equals J plus something del D del T. That equation, I have used the constitutive relation to write E and D and H in terms of B and instead of E and B respectively, and then the J, the free current, I have replaced by the ohmic formula, Ohm's law, sigma E. Okay, so we get this kind of an equation, the Ampere Maxwell law. Now we also have the continuity equation that the free charge should be conserved, which is given by this formula. Now if you plug in, this is the first order differential equation, and you can show when J is constant, for example, it doesn't vary with time, with space, when this term is 0, you can show that del rho del T equals something given by this formula, okay? So this is the, let me just think about it. Oh, I'm sorry. So, right, so divergence of J. So what you have to do is plug this here. Plug divergence of J free. We know J free by Ohm's law is equal to sigma times E. So this will be divergence of sigma times E, and sigma is a constant, so I can take it out of the divergence. So sigma times divergence of E. But divergence of E is nothing but rho free. So sigma rho free divided by epsilon equal plus del rho del T equals 0. And that equation can be easily solved, and because it has damping, and there's also a growing solution, but the solution is this. Okay, so because the rate of change is equal to proportional to itself, on the minus of itself, when you transfer it on the right hand side, what you get is that the total charge will quickly dissipate with time. Any volume charge density at time t will exponentially fall. And since sigma is a large number, while epsilon is also large, but you can think of it in CGS when epsilon is an order 1 number, but sigma is still very large, which means in a very short time, this conductor all the volume charge will dissipate. The charge quickly dissipates inside. Entire charge will come out to the surface. Okay, so this is good. This is something which we learned in electrostatics as well. Any volume charge inside was 0. So it seems like it happens when you have EM waves in conductors as well. It cannot have any volume charge. Actually, not EM wave, we just use Ohm's law in conjunction with the Maxwell equation. So even for an ohmic conductor, what we find is that amount of volume charge is very less, and within a few cycles of this time, any volume charge will go to 0. So ultimately, this rho free will become 0, and we have to replace this equation by the homogeneous version of Gauss law, divergence of E equals 0. Rest of the three equations remain the same. So these are the equations, effective equations, Maxwell's equations for inside a conductor. Okay, the only difference with the dielectric is this term. So, but this term will make a hell of a difference. It's going to make a hell of a difference. We will see in dielectric this term was not there at all, and this led you to a wave equation. Here we will see that it will lead to a wave equation, but with a twist. So let's take curl of this equation, one of these equations, these two equations, and what you will find is that it doesn't lead you to exactly wave equation. So it's actually this wave operator is there, del square minus 1 over velocity squared del t square, acting on E or B, equals not 0, but there is a source term on the right hand side. So mu sigma times del E del t, or del B del t. So for a dielectric, when sigma is 0, this term was not there. However, for conductor, this term will be there, and this term will lead to a world of a difference. Let's see. So again, remind yourself what we did. Once we get to a wave-like equation, we try to plug in a plane wave ansatz. So let's put a plane wave ansatz. Now if we plug this plane wave ansatz, this will give me k square. So I put in k tilde. For some reason, we will see it will turn out to be complex in the end. But let's say for example, you didn't know that this would be complex, and naively you put this kind of a solution here, plug the solution here. What you get, del square will give you k square or minus k square, and then del t square will give you plus omega square, or sorry, minus omega square. So you have k square minus mu epsilon omega square equals mu sigma. This single derivative will pull one factor of I omega. So mu sigma I omega, mu sigma and then I omega. So we see that the equation we get is not a real equation. It has a imaginary. So this is the wave vector squared, this is the frequency squared, everything squared. This is giving us a complex equation. From that we can tell that k cannot be a real quantity, because square of it will not have an imaginary part. So that means k must be a complex quantity. So this is what I wanted to say. In conductors we have dissipative wave equations. So waves dissipate. The solutions are plane wave with amplitude declining in space. So let's see how that happens. So as I said, k is a complex number, so I will write it in this form. Complex number is real part plus I kappa. Kappa is the imaginary part. And then we can plug it in this equation and solve for real and complex parts, real and imaginary parts on both sides. What you will get is some expression which simplifies when sigma is larger than everything else. For example, this is larger than 1. Everything simplified. This is larger than 1, this one. So you'll get this expression, okay? So you have this plus I times the same quantity, and when you plug it back here, what you get is exponentially diminishing solutions, because e to the I kappa times iz will give you e to the minus kappa z. So kappa, the term kappa will cause some kind of dissipation. You will get e to the minus kappa z. Then maybe I have the formula somewhere. Yeah. So the formula will be something like that. So there will be a real part of the wave, but the amplitude of that will depend on this quantity kappa and z. So e to the minus kappa z means if you look at the z profile, it will be exponential decay. So the fact that EM waves cannot make too much progress in a conductor is known as skin effect, right? As I said, skin effect. In fact, it is given by inverse of this length. This is the frequency. This is the wave number, complex part, imaginary part of the wave number, and inverse of that is the characteristic length scale, after which you don't have much of a wave left anymore, because the amplitude quickly gets to 0. So 1 over kappa. So this is an important quantity for a metal. You can compute looking at values of tables for sigmas for various different metals, and you'll see this is a very short wavelength. I think within a few centimeters or something like that. I have to check what typically this value is, but the impression I have is from few micrometers to few centimeters, the wave will completely dissipate. And unlike steady currents, where you can have J and E to be non-zero inside a conductor, for AC currents or fluctuating E and B fields inside a conductor, we see that we get back the same phenomena as electrostatics. That is, there cannot be much of an electric field inside, there cannot be volume charge inside. So it's a bit reminiscent of electrostatics. Also, another consequence of this fourth equation, which is the Faraday Law, another consequence of Faraday Law is that E and B, initially they were in phase in vacuum or dielectric. For conductor, due to the dissipative effect, they will cease to be in phase. The reason is that, let me just go back to the dielectric formula and then it will be clear why. So B is typically given by this formula. So the amplitude and phase of both sides should match, and this is a real quantity. The phase of B and E were the same. However, in case of conductors, the wave vector is a complex quantity we just saw. So then when you take a product of two complex quantities, the phase actually gets added up. So it's not the same phase of E, but it's the phase which is the sum of both of these two. Here, so this is the formula for B, and we can see the product of two complex numbers, hence the phase cannot be the same as E0 tilde. But you can take the magnitude of both sides, ratio of magnitude, and what you'll find out is that this gives you the magnitude of this. This is a number which has oh, I probably missed this. That Gauss law, or no sense, this law, divergence of E and divergence of B is 0, still means that in conductor we have transverse waves. That is something which you take for granted, but maybe we should not, and we should keep in mind why that happens. That is because of Gauss law and no sources and Sinks law for magnetic fields. That's why they are transverse. Then we were looking at this formula, and we took the magnitude of both sides. By magnitude, I don't just mean the vector magnitude, I also mean the complex, in the same sense of complex analysis. So this number will give you 1, and then the ratio of the amplitude will be just this guy. This is not an amplitude, this is, well, you can include this in the amplitude, but it doesn't. When you take the ratio, this guy gets cancelled out. Actually, it doesn't cancel out, I'm sorry. So I'll have to think a little bit. Right, I'm mistaken. So this represents the, so this is B0. This is the quantity B0, the amplitude, and then the rest is same as the electric field. So magnetic field has a diminishing space. In the spatial direction, there is a decline, and then there is a phase. So this is the dissipated wave, and then the coefficient of that is the this is the amplitude, so which is this. The ratio of the B and E amplitudes is just this quantity, the magnitude of K and omega, and which in the limit when sigma is larger than any other quantity can be written in this way. Okay. So this is the lag of phase. You can compute the phase difference between E and B from this formula. From this formula, you know what is the phase. It will just get added by the phase of this guy, which is just the ratio of the imaginary part of K and the real part of K, right? So the difference comes from the imaginary part of K. So next we talk about reflection and transmission of wave at a conductor surface. Now what we're talking about is a situation in which, let me just go back to the diagram. Yeah, so this guy, what we have here, we had two dielectrics. Now we're considering one dielectric and the other side is a conductor. So EM wave is traveling through a dielectric and it is incident on the surface of a conductor. Let's see what happens. Great. So again, so this interface equal to 0 is now an interface between a dielectric and a conductor. And so this is the equations. These are the boundary conditions. Most of you are familiar with this. So medium 1 is dielectric and medium 2 is a conductor. You can solve this equation that we have done before and obtain the Fresnel equations, which will look something like this. Instead of alpha and beta, I'm using this quantity beta tilde, which is kind of the ratio of beta over alpha for the dielectric. But at this time the twist is that this can be complex. Remember, due to the complex wave vector, this can be a complex quantity, right? So this is a complex quantity. This beta is not the same as the alpha and beta we wrote before, but you can think of it this beta over alpha of the dielectric, that I would call that to be beta tilde, some quantity beta tilde. And beta tilde is a complex number, okay, because the wave vector appears here. Now for a perfect conductor, what happens is that beta will become infinite because it's proportional to k2. Let's say k2 is, I think, proportional to sigma. Yeah. So this is k is proportional to sigma, so this will become infinite. B tilde, well, these are all finite, but this grows without bound when you send sigma to infinity. So that means we can ignore the ones here, and the ratio will that of the minus 1. While this becomes infinite, it's 2 over infinite, that is 0. So there's no transmission, but full reflection. This minus 1 is because for phase change. Okay, this minus 1 is because of a phase change. The reflected wave has a pi phase change ahead. It is ahead from the, or behind, equivalently behind from the incident wave by a phase pi. Okay, so from a perfect conductor you have full reflection with a pi phase change and no transmission. That is why most of you know conductors are excellent reflectors. Most of the metals you see are very shiny metal sheet unless there is some coating which forms on it. Mirror, most of you know, I've seen a mirror. It's made up of mercury, the surface of the mirror, and then there's a glass which is put on top of the mirror, which is just to cover the or protect the mercury. So this is something which you're familiar from childhood, but I guess now you know why. Again, it's just an artifact. It's just a consequence of Maxwell equations and EM waves. So we will stop here, and next class we will pick up. We will discuss some more optical phenomena, which have to do, which will be explained by Maxwell's equation very nicely. For example, dispersion. So we will talk about the theory of dispersion tomorrow when we meet. Okay, thank you. Please send in your queries and clarifications which you are having in this class through email or via Skype or Google Meets. I'll be happy to answer them. Go through the chapter, skim through it. I think things will become much more clear when you read something than you listen to a lecture and just forget about it. If you go after listening to the lecture, if you read the book, chapter of the book, I think things will become much more clear and obvious. And the book has many more supplementary details as well. Okay, I'll stop here and get back to you tomorrow.